This is the first video on predictive control, and we start with an introduction. First then, what is predictive control? Well, in simple terms, it's a very widely implemented technique in industry, and hence it should be of large interest to all graduates for whom control may form part of their studies. Now, some of the key aspects that you need to understand or appreciate are that predictive control describes an approach. It does not describe a specific algorithm, and that's a common misunderstanding among students. It's a way of thinking, a way of approaching problems. Now, what a user should do is interpret the approach for their own specific needs, and what that means is the actual algorithm you use may vary depending upon the context. So an off-the-shelf algorithm may not be a good choice in many cases. So what are the implications of this? It's less important that students learn specific details of any given predictive control algorithm, and what's more important is that they understand the key concepts. What is predictive control? Why does it work? How does it work? Etc., etc. So, why is it done the particular way that it's done? What is the impact of uncertainty, and how might that change depending on the context? How does the algorithm change when you include constraints? And again, how might that vary with the context or the nature of the constraints? What are the tuning parameters, and how do I use them? And which choices are poor and why? And again, how does this change depending on the context? And so on. So lots and lots of questions here, and you'll see what we're saying is that you have to focus on the key concepts, the key questions, or critically, understanding. If you understand how predictive control works, you're far more likely to make a good implementation. So what's the purpose of this lecture series? What we're going to do is focus on concepts. We want to know, why is predictive control logical and systematic? Why would I expect it to be a good technique to use? And what are the consequences of taking a systematic control approach or concept like predictive control and turning it into the mathematics that you need in order to implement it on a computer? So what we're saying is you've got certain concepts, certain way of thinking and approach to problem solving, and that is predictive control. But what you haven't necessarily got is specifically the mathematics or the code for putting that on a computer, because the mathematics and the code may vary depending upon the concept. And so if you understand what predictive control is, you should be able to do the mathematics fairly easily. You want to know things like what assumptions or design choices are implicit in a well thought through algorithm. And here's a key summary. A key to effective implementation is a good understanding of how MPC works. If you don't understand MPC properly, you're likely to implement it poorly, and the literature is full of relatively poor implementations by people who've just taken an off-the-shelf algorithm but not really understood it very well. So why is predictive control logical? Well, many effective control strategies have their origins in human behaviour. And what you'll notice is that humans are actually quite good at control, at least to some level, and so if we can understand how humans behave, then we've got a good start point for designing an automation technique. Let's take an example. If you look at something like PID and you deconstruct what's going on inside a PID compensator, you will find that actually it's a simplification of a human technique for controlling simple systems. Now, in a similar way, you can show that humans make use of predictions for common control strategies. So if you can understand how humans use predictions in order to control the world around them, then you're most of the way to actually automating that and getting a computer to do the same thing for you. Now we're going to use some examples, and that will make this a bit clearer. Driving a car then. What is a core component of driving? Well, this is what drivers do. They look ahead, and the key word in this is they anticipate future targets or demands. So typical things they'll be looking for: does the road change? Is there any turns? Is there any obstacles? Are there any pedestrians? Are they on the road? Are they about to step onto the road? Are there other vehicles? These could be parked or they could be moving. Or do I have to change my trajectory in order to avoid them? Is there going to be a change in the speed limit at some point, and how should I act? And the key thing here is you'll see this word anticipate. What we're doing is we're anticipating all the future obstacles and targets and using that in order to update our plans. So humans use anticipation, and an equivalent word, of course, is prediction, to help them determine effective control strategies, certainly when they're driving. What about racket sports then? So what's a core component of badminton? Now, anyone who's played a racket sport will probably understand this. Good players will plan several shots ahead in order to move their opponent into a weaker position. Okay? Or, alternatively, to prevent themselves being put in a weaker position. Once you've got the opponent in a weak position, you're then able to maybe punish them and win the rally. So what might they do? And here's the key thing: they will predict the impact of different shot choices and select the ones which lead to the most desirable outcome. So again, what do you notice? Racket sport players are using anticipation or prediction to help determine effective control strategies. Now we've got a little video here to demonstrate this in action. You'll see two players here, and you'll notice how the player in black basically manipulates the other player into a gradually weaker position and eventually wins the rally. So here we go. It's we need to get rid of that. Right, here we go then. Play. Hopefully that wasn't too long, but you saw how the darker player, the one in black, basically kept pushing the other player into a weaker and weaker position until the other player could not recover, and they were using anticipation. What about filling a tank to a desired level? So what's a core component or human strategy if you want to fill a tank? And you might call that tank level control. And again, you'll see we've got the same sort of technique. What we're going to do is observe the change in depth and anticipate how the depth changes in the future, and we're going to use that anticipation, that's the key word, in order to modify the input flow in order to ensure that the future depth does not exceed the target. And again, you'll see the key word here again is anticipation or prediction. So again, we've got an example which will help you see what's going on here. If I can just find the example, there it is. It's a simple MATLAB GUI. So if I run that, so here's the GUI. So you can see we've got a tank, and what I'm going to do is start filling the tank, and you'll see if I do nothing and just let it fill, it fills very quickly and it overflows. Okay, so what I want to do now is say, alright, if you were filling it yourself, what would you do? So I started and I say, oh, it's filling quite fast, and you see I gradually slow down the rate at which it's filling. Slow it down, slow it down, slow it down, slow it down. I've stopped it a bit too soon there, so then I might go up a bit. Okay. It's gradually filling, you can see it's gradually filling, and then I might stop. So what do you notice? A typical human strategy, I've pressed start again, we keep changing the input flow rate, okay, so that it doesn't overflow. Alright, now how is it we do this? Well, let's have a look at this plot over here. So what we've done in this particular plot is we said, let's imagine the situation once we got to a time t equals 3 seconds. So this black diagram shows effectively what is happening to the depth. The red line shows the target depth, and the blue line shows the flow going in. Now, if you were basically observing these lines, when you got to this particular point here, what you would be doing in your head is you'd be saying, I'm expecting the depth to keep following this black line. So I can see at some point in the future, I'm going to reach the target and then overflow. And because the gradient's quite steep, you're going to anticipate you're going to overflow. So what would you do? You would say, what I need to do is start reducing the input flow. So you can see how I'm marking this blue line here. You need to start reducing the input flow. And if I do that, then the rate at which it fills will start to reduce. And in essence, you'll come up with some sort of flow diagram where the flow comes down to 0 and at the point that you get to the target. But the key thing here is you can see how humans use prediction. They see how is the tank filling and where do I expect it to be in the future, and therefore how do I modify my input down here in order to make sure I don't overflow. Okay. So an interim summary for you. It's clear that humans use anticipation, or prediction if you prefer that word, okay, in order to consider the impacts of different control strategies. And we choose the strategy that basically we expect, and that's an important word, expect, we can't guarantee, to give the most desirable future outcome. And therefore, prediction underpins practical human control strategies, and therefore you might say it seems a logical concept to incorporate into any automated strategies. Now, just to finish, why might you want to look at a video series or course on predictive control? So far we've given a relatively superficial view on why the use of prediction seems logical, and you can list many other advantages of predictive control which motivate further study. So here are some of them. It's an intuitive concept because you can relate it to human behavior. It's relatively easy to understand, again because you can relate it to human behavior, and it's also relatively straightforward to implement on a variety of systems. It allows systematic handling of constraints, which most other control strategies do not. It handles multivariable systems and dead time without any modification. In essence, they come for free. It also implicitly includes some sort of feed-forward to make good use of future target information, and you'll find typical strategies it's not quite so implicit. And finally, it handles challenging dynamics. You'll find strategies a bit like PID are very good for first order, second order systems, things of that nature, but as soon as you put in difficult dynamics, PID is not quite so effective. So why is predictive control popular in industry? And the answer is relatively simple. It's been proven to improve profits quite significantly because it gives superior control. It's as simple as that. I'm getting better control and therefore I'm earning more money. Now, why it does that or how it does that, one of the most obvious arguments you'll see in the literature is that because it gives you better control, what you can do is reduce the variance of the output because you've got better control. And if you reduce the variance of the output, then you can operate closer to any constraints in the system. And if you can operate closer to the constraints, you can either increase the output quantity or the output quality, and therefore make more money. Now, implicitly within this is the ability to incorporate constraints into the approach explicitly, means that you can have optimum constrained performance. Alright, and this is as opposed to if you're using things like PID, you'll find that the way they deal with constraints is much more in an ad hoc fashion, so not nearly as optimized.